This is a Roman wall painting. In looking at their artwork, much of it comes to us from towns like Pompeii that were in some way covered, in that case with the eruption of Vesuvius in 79 AD, and covered with volcanic ash but preserved from the elements. Take a look at this and we'll see here, first of all, it's a rather natural pose. A woman clothed in some type of cloth wrap here, gathering flowers. The position of her legs, she's obviously walking, and she's looking down here and picking a flower with this hand. What kind of pigments did they use for this is a really good question. Greeks benefited from what the Egyptians had learned about manipulating earth colors and heating them and mixing them together and creating other kinds of chemical compounds. The Romans no doubt benefited from what the Greeks knew in that way. In the quest for greater colors, two features of colors that are of relevance. First of all, how color fast are they? Will they fade very quickly with sunlight? So color fastness is one aspect of pigments and colorants. Another one is toxicity. Various chemical compounds might have contained chemicals like arsenic or mercury and would have had the nasty side effect of perhaps being unhealthy to get too close to or to touch or even to inhale fumes from them. This is the trade-off that some people put up with that type of toxicity in order to get the kind of colors that they were interested in getting. We'll see that as time progresses, various types of knowledge are brought to bear to eventually, in our modern times, create pigments that are non-toxic and very color-fast. Colors were sometimes difficult to achieve and difficult to make in a color-fast way, and if you could achieve them, perhaps rather dangerous to be around. And just another picture that Gombrich illustrates here of a Roman wall painting, in this case a faun, some type of a mythological creature here. What's interesting about this is that you're seeing here some attempt to give shape to a face and a head that we know to be circular by the way that more light is being reflected here by the closer surface and then shading going around this way. That's a technique that was pretty much lost until rediscovered in the Renaissance, and that's one of 5 different types of perspective to give a 3-dimensionality to a 2-dimension surface. And we'll see a lot more of that as we move into the next unit. Here we see a Roman wall painting, and it's pretty apparent that there was an attempt here to give some sense of distance. One of the ways that distance is illustrated, and you get the psychological sense of it, is that things in the distance may seem fuzzier or more washed out. That may just be accidental in this case. They may not have realized that that's a type of perspective. Some attempt to give some sense of distance by way maybe of making some objects recede in the distance and be smaller. It doesn't look like it's too well carried off here. Here's an animal, and some distance away another one about the same size. That doesn't give us a very good feeling about this animal being farther away, because you'd expect the farther away one to be somewhat smaller. Maybe if we studied this carefully, we would get some idea of that by the size of these figures. People here being about that size, and people here being much smaller. To make some semblance of distance, the idea of distance, but nothing so well organized as to do that in a methodical way. And that methodical way, which is something we'll take a look at next time, is something that comes along much later in history, about actually 1,500 years beyond this point in the Italian Renaissance. Now let's take a look at these solids. In one of the assignments last time, you actually folded these up and made them. These are all synonyms. Let's refer to them as the perfect solids, although these other names, Platonic solids, regular polygons, and polyhedra, might also be applied to them. The starting point for all this is to understand how a circle is derived. Some point and the same distance from that point swept around and meeting itself defines a circle. If we were to spin that in 3 dimensions, we would get a sphere. But in this case, it's enough just to regard this as a circle. Now, pretend that we have 3 magnets here that are all trying to push away from each other, and this is a circular track. And we put these magnets on their own little wheels, and they naturally try and get themselves as far apart from one another as possible. If we achieve that, then we would have 3 equidistant points on the circumference of this circle. Now, if we join them together, we get a triangle. An equilateral triangle, the sides are all of equal length. And this is something the ancients figured out. Now, if we put 4 points equally spaced around the edge of a circle, we would of course get a square. And if we did 5 points, we would get a pentagon. And 6 points, we'd get a hexagon. These types of shapes were explored in just this way by the ancients, and then various things were done to sort of manipulate them and come up with other ideas. Well, if we join various points together like this, well, now we seem to get 6 equilateral triangles. One reason the ancients did this is they felt that they were locked into these kinds of shapes and these kinds of three-dimensional structures, if you spun them out to 3 dimensions, like riddles built into these things. They were the way they were because the gods who created the place left them as little things for us to solve. And because it was important to curry the favor of the gods, it was thought by some to be important to figure these things out, because that was a way to communicate back to the gods that you understood the riddle. So let's go back to the sphere now. There's a method by which, following the same thing we had just done with the circle in 2 dimensions, that we could derive 3-dimensional shapes. And I'll show you how that was done. These are the shapes that are derived by the mechanism that we'll talk about in a minute. They're called the perfect solids because they all share a characteristic. Well, 3 characteristics, in fact. One of the characteristics is that the vertices, if you stand at any one of these, you get exactly the same view of receding lines. The lines recede at the same angle. Another characteristic is every face is identical to every other face. Identical meaning not just the same shape, but exactly the same size. A third characteristic is that if you stand on any edge, every angle here will be identical. So this angle here is the same as this angle there, this angle there. In this shape, this angle, this angle, this angle, they're all the same. So those 3 characteristics are kind of important, if for no other reason than to just remember that that defines a perfect solid, and it's been proven, and the ancients had some inkling of this, that these were the only 5 shapes that met that requirement. No matter what other shapes you came up with, you would never find any others that had those 3 rules all apply to them. So what does this tell you? Well, perhaps here's another riddle. That if we figured this out, the gods were trying to communicate something to us by this. These shapes maybe had some significance. Or maybe it was important for us to figure this out because it reflected back a greater understanding of the riddle that the gods had posed to us. So went the thinking of the ancients. Now, how would you derive these? In a very similar way, suppose you started with a sphere and you put 4 points on it. Let's suppose they were naturally repelling magnets, and they spaced themselves out to be as far apart from each other as they could possibly be. And then you connected them in a 3-dimensional way. What you would come up with here with 4 points was a tetrahedron. Now the circle, the sphere around it has been removed. This may look like a pyramid, but it's not. It's not because if we could see that unseen side to it, there really are only 3 sides pointing up, not 4. The base of this is not a square, but it's a triangle. If we did 6 points on the surface of a sphere, all equally spaced as far apart from one another as they could, we would get an octahedron similar to tetrahedron, except the base of this, of course, is triangular. And here, if you were to cut this octahedron in half, you would in fact have a pyramid because the base in that case would be a square. If we started with 8 points on the surface of a sphere, all equally spaced from one another, and then connected them and stripped away the outside sphere, we would get a cube. And in this case, if we did the same with 12 points, this is the way we would derive a dodecahedron. Now here, I managed to find an illustration that rotates, which makes things kind of more interesting. You see pentagon faces here, dodecahedron, 12 faces, and icosahedron with 20 faces, same sort of a thing, 20 dots on the surface of a sphere, all equally spaced, all the same distance apart, and it defines this 20-sided object. So you've already folded these up. You have an idea, in having touched them in 3D, what they look like. Another thing the Greeks did with them was to associate the elements that they thought made up the world and everything else that we saw out there. They would associate them, fire, air, earth, and water, plus the stars in the heavens. There were 5 of those. So they associated the shapes with those and thought that, well, with this kind of a correlation between them, certainly this meant something, and maybe we understood more about the way the world was made up and the universe was made up by having done this.